Welcome to all of you. Today we discuss MCQ 2023 on real analysis paper CC-5 Mathematics Honors, University of Calcutta, semester 3 under CBCS. Question paper 2023 Mathematics Honors CC-5. Question 1a. Limit x tends to 0 sine box x whole divided by x equal to what? Does not exist. Option 4. Here we assume x not equal to 0. Now box x, that is the floor x, this equal to 0 when 0 less than equal to x less than 1. Actually this is the box x function, 0 less than equal to x less than 1, and this is equal to minus 1 if minus 1 less than equal to x less than 0. For right hand limit x tends to 0 plus sine of box x by x, that is limit x tends to 0 plus sine 0, when 0 plus sine box x is 0, so sine 0 by x, this is equal to 0. And for left hand limit x tends to 0 minus sine box x by x, sine box x when x tends to 0 minus this minus 1, so this minus of sine 1 and 1 by x, x tends to infinity, actually x tends to infinity, x tends to 0 minus 1 by x function tends to minus infinity, so this is equal to infinity. So right hand limit not equal to left hand limit. Correct option is 4. Alternatively, you can, using by sequence, consider an arbitrary neighborhood of 0, say neighborhood of 0 with delta equal to 1, that is minus 1 less than x less than 1, and fx equal to sine of box x by x. Consider the sequence xn by xn equal to 1 by n plus 1 for n belongs to the set of all natural numbers n within the interval minus 1 less than x less than 1. Then the sequence fxn equal to sine box of 1 by n plus 1 whole divided by 1 by n plus 1. So obviously when n equal to 1, this 1 by 2 sine of box 1 by 2, so this equals to 0 by half, 0 by 1 by 3, 0 by 1 by 4, so this sequence tends to 0, converges to 0. Next, consider the sequence yn defined by yn equal to minus 1 by n plus 1, n belongs to the set of natural numbers within the interval, open interval, minus 1 less than x less than 1. Then sequence fyn equal to sine box of minus 1 by n plus 1 whole divided by minus 1 by n plus 1, this is equal to sine of minus 1, because if we put n equal to 1, so this is equals to minus 1, sine of minus 1. So if we put n equal to 2, we get sine of minus 2, sorry, sine of minus 1 by 2, that is sine of minus 1. So taking common sine of minus 1, and from this part this minus 1 by 1 plus 1 2, so this minus 2 minus 3 minus 4 and so on. So this tends to minus infinity, and this the sine of minus 1 means minus of sine 1, so minus minus plus, so this tends to actually plus infinity. Thus we have two sequences xn and yn in the open interval minus 1 less than x less than 1, both converging to 0, but the sequences fxn tends to 0 and sequence fyn tends to infinity. Then limit x tends to 0 fx, that is limit x tends to 0 sine of box x whole divided by x, does not exist. If we draw this function, this Desmos graph, sine of floor function x by x. So we can find this graph neighborhood of 0 from the 0 plus, that is the 0 plus sine of box x by whole divided by x, this tends to 0, and when 0 minus limit x tends to 0 minus left hand limit, sine of box x by x tends to plus infinity. So we can find this by Desmos nature of this graph neighborhood of 0. So obviously correct option is 4 does not exist. Next question B. Let fx equal to 1 by sine x, x belongs to the open interval 0, 1 and 5 when x equal to 0, fx equals to 10 when x equal to 1, then f does not have a limit at what? Fx equal to this, now fx x tends to 0 plus the right hand limit of fx. So right hand limit of fx is this, x tends to 0 plus, this equals to x belongs to 0 to 1 open interval. So right hand limit from right hand limit x tends to 0 plus, we have the function 1 by sine x. This 1 by sine x, actually this is the 1 by sine x tends to infinity from the right hand limit, and f0 equal to 5 because here fx equals to 5 at x equal to 0, and the left hand limit of 1, left hand limit of 1 actually left hand limit of 1, actually function is defined within the open interval 0 to 1. So left hand limit of 0 we have not calculated the left hand limit of 0. So left hand limit of 1.1 that is left hand limit of 1 is this. Also limit x tends to 1 minus 1 by sine x, this equal to 1 by sine 1. So clearly f does not have a limit at x equal to 0, x equal to 0. Otherwise function is continuous except the point 0, infinite limit here. Actually by Desmos app, if we draw this graph 1 by sine x, 1 by sine x for x equals to 1 up to minus 1 to 1. So we get this graph minus 1 to 1. So x 1 by sine x, this 1, actually here fx is defined for the open interval this 1 by sine x, and for x equal to 0 this is equal to 5, and x equal to 1 this is equal to 10. So when x equal to 0 fx equal to 5 and x equals to 1 this equals to 10, this point is 10 defined here. So if actually the right hand limit of 0 is the infinity, but value of f0 equal to 5, so f does not have a limit at x equal to at 0, at the point 0. Correct option is 1. Next question. A, B, C. Question C. Fx equal to e to the power 1 by x minus 1 whole divided by e to the power 1 by x plus 1, x not equal to 0, this is equal to 0 when x equal to 0, has discontinuity at x equal to 0. The type of discontinuity is what? Now put y equal to 1 by x. Then from the given function fx equals to e to the power y minus 1 by e to the power y plus 1 equal to 1 minus e to the power minus y whole divided by 1 plus e to the power minus y equal to 5y say. Clearly x tends to 0 plus, because if we draw the graph 1 by x, so when x tends to 0 plus, that is the right hand limit, y tends to infinity, and x tends to 0 minus, so left hand limit at the point 0, so y tends to minus infinity. So limit x tends to 0 plus fx, then limit y tends to infinity, 1 minus e to the power minus y by 1 plus e to the power minus y. So 1 minus e to the power minus infinity, this equals to 0, because this graph of e to the power x is this. So e to the power minus infinity tends to 0. Actually this limiting sense, this 0 by 0, so this is equal to 1. And the left hand limit x tends to 0 minus fx, this equal to limit y tends to minus infinity. For this x tends to 0 minus, y tends to minus infinity, e to the power y minus 1 by e to the power y plus 1, e to the power minus infinity 0, so this 0 minus 1 by 0 plus 1, so this is equal to minus 1. So we get the right hand limit is 1 and left hand limit is minus 1, so not equal. Left hand limit and right hand limit and left hand limit x tends to 0 if x does not exist. Here f0 equal to 0, because this fx 0, this x when x equal to 0, and this type of discontinuity is called the jump discontinuity. So correct option is 2, jump discontinuity. E to the power 1 by x minus 1, e to the power 1 by x minus 1 whole divided by e to the power 1 by x plus 1. E to the power 1 by x minus 1, e to the power x plus 1. So we get this is the function x limit from x equals to 1, x axis limit, set we limit this, and y axis limit is to 2. So this is the graph for this function e to the power 1 by x minus 1 whole divided by e to the power 1 by x plus 1. For this graph, this graph is this, right hand limit is this 1 and left hand limit is this minus 1 for this graph. The correct option is 2, jump discontinuity. Now we shortly discuss the different types of discontinuity at an interior point C. Here f is a function defined on an interval AB, real valued function, and C be an intermediate point, and we use here notation limit x tends to C minus this f of c minus and limit extends to c plus fx equal to f of c plus. There are three types of discontinuity: first kind discontinuity, second kind discontinuity or oscillator discontinuity, and infinite discontinuity. First kind discontinuity or simple discontinuity, there are two types. Left hand limit equal to right hand limit is called removable discontinuity. Here function f is defined at the point interior point c or may not be defined at the interior point c. Consider this example: fx equals to mod x for x not equal to 0 and fx equal to 5 for x equal to 0. So clearly left hand limit is 0, right hand limit also 0. The function value at the point 0 is 5. So function is not continuous at the point 0, and this type of discontinuity is called removable discontinuity. If we define fx equal to 0 for x equal to 0, then this fx is continuous at the point 0. So this is called removable discontinuity. And next type discontinuity under first kind, left hand limit not equal to right hand limit. This type of discontinuity is called jump discontinuity. F is defined or not defined at the interior point c. Signum function x, this is equal to 1 when x greater than 0 and 0 when x equal to 0, minus 1 when x less than 0 equal to 0. So left hand limit for this function at the point 0 is minus 1 and right hand limit at the point 0 for the function is 1. So this is the jump. This jump 1 minus 1 to 1. Jump is 2. Jump is 2. Next, second kind discontinuity or oscillatory discontinuity. F must be bounded function in some deleted neighborhood of C. Deleted neighborhood of C, if we delete this point C and the open interval C minus delta, C plus delta, except the point C for some positive delta. At least one point if C minus and if C plus, left hand limit and right hand limit does not exist. When if C minus actually is the limit superior for the right hand limit, f upper bar C plus 0. Actually this means limit C tends to extends to C plus, upper bar, limit upper bar. When this limit superior and limit inferior right hand limit equal, then fc plus exists, and this is the value of this. And similarly for left hand limit we get limit superior f upper bar C minus 0, f lower bar C minus 0. So these four limits exist finitely because this function is bounded function. And either fc plus 0 not equal to fc plus 0 upper bar not equal to fc plus 0 lower bar. That means fc plus 0 does not exist, or fc minus 0 does not exist. That means fc minus 0 upper bar not equal to fc minus 0 lower bar, or both does not exist. But function is bounded. Example, fx equals to sine 1 by x. For sine 1 by x, this the f 0 plus 0 upper bar is 1, if 0 plus 0 lower bar is minus 1. Similarly, if 0 minus 0 upper bar is 1 and if 0 minus 0 lower bar is minus 1. This is the 1, this is the minus 1. This function is bounded function because it's the sine 1 by x bounded between the interval minus 1 to 1. So this type of discontinuity is oscillatory discontinuity. Actually, if we draw this graph in the small graph, sine 1 by x, sine 1 by x, and this is the beautiful function is this is the 1 is the minus 1. If we expand this, 1 to 1 limit. So this is the graph of sine 1 by x. This is the function sine 1 by x bounded function, and this left hand limit or right hand limit does not exist, but function at the function sine 1 by x bounded function, but left hand limit and right hand limit does not exist at the point x equal to 0. This type of discontinuity is called oscillatory discontinuity, second type of discontinuity. Next, infinite discontinuity. If f is unbounded on neighborhood of c, that is at least limit superior c plus 0, f c minus c plus 0 lower bar, limit inferior c plus 0, limit superior c minus 0, limit inferior c minus 0 is infinity or minus infinity. Example, fx equals to 1 by x. So x not equal to 0, 1 by x, and 0 is equal to 0. So limit upper bar 0 plus 0 equal to limit lower bar 0 plus 0 equal to infinity. Is infinity. And similarly 0 minus 0 left hand limit, superior limit superior for left hand limit, and inferior for minus infinity. So 0 is the point of infinite discontinuity. So for this function 1 by x, infinite discontinuity exists at the point x equal to 0. And infinite oscillatory discontinuity, if one or both of c plus 0 upper bar and c plus 0 lower bar be infinite, and if c plus 0 upper bar not equal to f of c plus 0 lower bar, that is, f has infinite oscillatory discontinuity at the right of the point c. Similarly, we can define f has infinite oscillatory discontinuity at the right and c, at least one or both be infinite, c minus 0 upper bar, c minus 0 lower bar, and at least one of these upper bar lower bar not finite, and they are not equal. They are infinite. At least one of them, one or both this infinite, and this upper bar and lower bar not equal. Then infinite oscillatory discontinuity at the left of the point C. So this is the jump discontinuity. Correct option is 2. Next, question D. Which statement is true for the function fx equals to 3 plus 2x minus 3 by 2 less than x less than equal to 0, 3 minus 2x 0 less than x less than 3 by 2. First we draw this graph 3 plus 2x and 3 minus 2x. This interval minus 3 by 2 less than x less than equal to 0. So less than minus 3 by 2 to 0 less than equal to 0, and 3 minus 2x 0 less than x less than 3 by 2, 0 less than x less than 3 by 2. Now we want to check the continuity at x equal to 0. For this, first we find the left hand limit of fx, limit x tends to 0 minus fx equals to this 0 minus, so 3 plus 2x is equal to 3. Actually this is the value of the f of 0 minus 0, and the right hand limit, this equals to fx equals to actually 3 minus 2x. So this is the 3 3 minus 2x. 3 minus 2x. This is equal to 3. And f of 0 this is equal to 3 plus 2x, because this equal to 0 for 3 plus 2x. So fx is continuous at x equal to 3. For the differentiability, does not exist, because the left hand derivative, this limit x tends to 0 minus fx minus f0 by x minus 0, this equals to 2, and the right hand derivative is this at the point 0, limit x tends to 0 plus fx minus f0 by x minus x0 is equal to minus 2. So not equal, so f is not differentiable at x equal to 0. So correct option is 2. F is continuous at the point 0 but not differentiable at x equal to 0. Correct option is 2. Question E. If f is a monotonic function defined on an interval I, then identify the monotonic function on I. Mod f, f square, f cube, f square minus f. Actually, correct option is 3. F cube is monotonic on I. First we define what is the monotonic function. A function f maps from the interval I to R is said to be monotonic on the interval I if f is either monotonic increasing throughout the interval I or throughout the interval I monotonic decreasing. So for monotonic increasing or non-decreasing function, this is the graph for the monotonic increasing. X less than equal to y implies fx less than equal to fy for all x comma y belongs to the interval I. If we put here only less than, then it is strictly monotonic increasing function, and this is the graph for monotonic decreasing function, non-increasing. When x less than equal to y implies fx greater than equal to fy for all x comma y belongs to I. But this function, this non-monotonic function, piecewise monotone, for this up to this piece, from this part to this part is monotonic decreasing, from this part to this part monotonic increasing, from this part to this part monotonic decreasing. But this function is not monotonic throughout the interval. So remember this. Consider example fx equal to x, monotonic increasing function. So fx equals to, if mod of x, this is not monotonic within the interval -1 to 1, because this part is monotonic decreasing, this part is monotonic increasing. And fx equals to f square, that is x square, this is the graph, this is monotonic decreasing and this part is monotonic increasing. And when f cube, this is equal to x cube, so actually graph is this x cube, this graph. So actually this function is monotonic on the interval -1 to 1. And next last f square minus f, x square minus x, x square minus x is the graph is this. So this part is monotonic decreasing part and this part is monotonic increasing part, so not monotone in the interval -1 to 1. So correct option is 3. F cube is the only monotone function. Question F. Let fx equals to sin x by x, x belongs to 0, pi by 2. Then fx is what? Actually this is the strictly decreasing function on this. sin x by x, sin x by x by Desmosel, sin x by x. So this is the graph sin x by x within the open interval 0 to pi by 2. This point 0, actually this point is pi, so this point is pi by 2. So for this part 0 to pi by 2. Clearly, f is continuous on the closed interval delta to pi by 2 for delta, some positive delta is continuous function. Next, we find the derivative of this function f dash x. This is equal to x cos x minus sin x whole divided by x square when x belongs to the open interval 0 to pi by 2. Now we know the inequality sin x less than equal to tan x when 0 less than x less than equal to less than pi by 2. Clearly, tan x greater than x, so sin x by cos x greater than x. This implies sin x is greater than x cos x. So x cos x minus sin x is less than 0 for 0 less than x less than pi by 2. So from f dash x, the numerator is less than 0 and this x square denominator is positive within this interval 0 to pi by 2. So f dash x ultimately less than 0 in this open interval 0 to pi by 2. So fx equals to sin x by x, 0 less than x less than pi by 2 is strictly decreasing function. Correct option is 1. Note that f maps from the closed interval ab to r, set of real numbers r, be continuous on the closed interval ab and f dash x greater than 0 for all x belongs to the open interval ab, then ab is strictly increasing function. Similarly, when f dash x is less than 0 for all x belongs to the open interval ab, then ab is strictly decreasing function on the closed interval ab. Here this is the inequality. By graphically we can set this is the sin x, this x and tan x, and this is the tan x, this is the x, this is the sin x. If we draw all this graph sin x, x and tan x, so we get this is the red curve is tan x and this is the straight line and this is the sin x. So within the limit 0 to pi by 2, this tan x is greater than sin x is less than x less than tan x. This red curve is tan x, this is the x and this is the sin x. Next question G. If limit x tends to 0, a sin x minus sin 2x whole divided by tan cube x is finite, then choose the correct value of a from the following. Actually correct value a equal to 2. Now this is the 0 by 0 form. So using L'Hospital's rule, differentiating the numerator and denominator, we get a cos x minus 2 cos 2x whole divided by 3 tan square x sec square x. If we put limit, if we find limit x tends to 0 from the numerator, a cos x minus 2 cos 2x is equal to a minus 2, and for denominator we get this limit x tends to 0 for denominator is equal to 0. So in order to that this limit is finite, to find the finite limit it is necessary that this a minus 2 must be 0. So a equal to 2, hence the correct option is a equal to 2. For interest, we want to find the limit this. If we put a equal to 2, we get this 0 by 0 form, and differentiating numerator and denominator, again we find this, and again this is the 0 by 0 form, again differentiating we get this. After simplifying we get this minus cos x plus 2 into 2 cos 2x whole divided by 6 to the power 6x plus 7 10 square x, and so on so on. So this 0, this is 1, this cos 0 minus 1 is 4 1, so we get this equal to, final limit answer is 1. If you find any mistake or wrong calculation, you must inform this. Next question is, which one of the functions does not satisfy the condition of Rolle's theorem in the closed interval minus 1 to 1? Correct option is 4, x to the power 2 by 3. First we draw the graph x to the power 2 by 3. So from this graph minus 1 to 1, minus 1 to 1, clearly this function is not smooth at the point 0, so we cannot find the continuous tangent from the left hand side to right hand side. So this is the point where f is not differentiable. F is continuous in the closed interval minus 1 to 1, but f is not differentiable at x equal to 0. Limit x tends to 0 minus fx minus f0 by x minus 0, this is equal to limit x tends to 0 1 by x to the power 1 by 3, this is equals to minus infinity. Left and right hand limit x tends to 0 plus fx minus f0 by x minus 0, this is equal to x tends to 0 plus 1 by x to the power 1 by 3, this tends to infinity. Actually this right hand limit, this tends to infinity, this tends to minus infinity, hence f is not differentiable at every point of the open interval minus 1 to 1. Therefore fx equals to x to the power 2 by 3 does not satisfy the condition, actually the second condition of the Rolle's theorem. So the correct option is 4. All other functions are satisfy the Rolle's theorem. Next question, fx equals to 1 minus mod x has maximum value at x equal to 0. One minus mod x, 1 minus mod x. And this is the graph, so function is not smooth at the point x equal to 0, this point. When fx equal to 1 minus x 0 less than equal to x less than infinity, 1 plus x minus infinity less than x less than 0. F is continuous everywhere on R. F is not differentiable at x equal to 0, because f dash x equal to minus 1, because this fx equal to 1 minus x, so f dash x is the minus 1, this less than 0 for x belongs to the open interval 0 minus delta comma 0, some positive delta, at the immediate left hand neighborhood of 0. F dash x is minus 1, slope is minus 1, and f dash x equals to, for right hand side, this 1 plus x, so differentiating we get this 1, this positive, for some x belongs to the right hand neighborhood 0 to 0 plus delta. So f has a local maximum at x equal to 0. Note the first derivative test theorem. Let f be continuous on the interval close to interval I, a to b close to interval, and c be an interior point of I. Let f be differentiable on the open interval a comma c and open interval c comma b. First, f dash x greater than equal to 0 for the left hand neighborhood of c, and f dash x is negative or 0 for right hand neighborhood of c. Then f has local maximum at x equal to c, and this is our case. This is the from the left hand neighborhood c minus delta f dash x is negative, f dash x is negative c minus delta to c plus delta, c minus delta 0 minus delta, and f dash x is less than equal to 0 for c minus delta to c, and f has local minimum. F dash x keeps the same sign, c minus delta to c, c to c plus delta. F has no extremum at x equal to c. The converse of the above theorem is not true. So f equal to this function has local max minimum at x equal to 0, but f dash x takes both positive and negative values on both sides of x equal to 0. So and this is the wrong, because this is the 0 to infinity. So actually this interval is this, and this interval is this. X belongs to 0, 0 plus delta. This is the right hand interval, and this is the left hand interval for this 0 minus delta, comma 0, because the left hand interval is this 1 plus x, so this is positive. So x, when f dash x equal to minus 1, that is less than 0 for the right hand neighborhood of 0, and f dash x equals to 1 greater than 0 for x belongs to the left hand neighborhood of 0. So for the left hand neighborhood, this is the positive, and right hand neighborhood is negative. So this is the local maximum. So option correct, local maximum is this. Next, last question, J, which is the one is the uniformly continuous on the indicated interval. Option 1 is the correct option, fx equal to x square on the closed interval AB and for a greater than equal to 0. Choose epsilon, pre-assigned as epsilon, positive epsilon. F will be uniformly continuous on the closed interval AB if we can find a delta greater than 0 such that for any 2 point x1, x2 in the closed interval AB, modulus of x2 minus x1 less than delta implies modulus of fx2 minus fx1 is less than epsilon. Now modulus of fx2 minus fx1 equal to modulus of x2 square minus x1 square. This equals to modulus of x2 minus x1 into modulus of x2 plus x1. This less than twice b modulus of x2 minus x1, and this less than epsilon. This less than epsilon, so this is less than delta. So twice b into delta is less than epsilon. That is delta equal to epsilon by twice b. So delta equal to epsilon by twice b. If we choose delta equal to epsilon by twice b, then for any x1 and x2 in the closed interval AB satisfying this modulus of x2 minus x1 is less than delta, and the inequality modulus of fx2 minus fx1 less than epsilon holds. Hence F is uniformly continuous on the closed interval AB for a greater than equal to 0. So correct option is 1. Now what is the difference between the continuity and uniform continuity? Continuity is the property of a function at a point, whereas the uniform continuity is the property of a function on an interval or on a set. Continuity is a local property and the uniform continuity is a global property. The definition of continuity: if A maps from I to R be continuous on an interval I, then for a pre-assigned positive epsilon there exists a delta, positive delta, such that for all x belongs to the neighborhood of C delta intersection I, inequality modulus of fx minus fc less than epsilon. Whereas if f maps from I to R be uniformly continuous on I, if for a pre-assigned positive epsilon there exists a positive delta such that for any 2 points x1, x2 in I, modulus of x2 minus x1 less than delta implies modulus of fx2 minus fx1 less than epsilon, and this delta depends on epsilon as well as the point C. Delta depends on epsilon and C. So if point C changes, then delta changes also. Whereas here for uniform continuity, delta depends on only C, not on the point C. Here delta depends on epsilon, and this delta works uniformly over the entire interval I. Actually, this delta is the infimum of this delta epsilon C. Note that if F maps I to R be uniformly continuous on I, interval I, this implies F is continuous on the interval I. If F be continuous on the closed and boundary interval I, then F is uniformly continuous on I. If F maps D to R uniformly continuous on the domain D, and if xn be a Cauchy sequence in D, then fxn sequence fxn is also a Cauchy sequence in R. F maps I to R be uniformly continuous on I if I be a bounded interval. This implies F is bounded on the interval, bounded function on the interval I. Thank you for watching this video.